In my previous video, I have discussed properties of isomorphism. At first I recommended you, please see my previous video. Then today's video will be so easy. Let's verify it. Consider a 2 cross 2 matrices 1A, 0, 1, where A be the member of capital Z, means set of integer, which is isomorphic to set of integer under addition. And since this matrix is isomorphic to set of integer, so this matrix will satisfy all properties of isomorphism. Let's see. At first consider a mapping phi from G to Z such that phi of 1A 0 1 equal to A, where for all A be the member of integer. Then phi of identity matrix would be 0 and 0 be the member of set of integer, and we all of us know 0 is the identity element of set of integer under addition. So identity element for G maps identity element of set of integer under addition. Now let's see phi of 1A 0 1 to the power n. If we multiply this matrix more and more, this would be similar to matrix 1 NA 0 1, and this is similar to NA by this defined mapping. So this property has satisfied here, because in isomorphism phi of A to the power n equal to phi of A to the power n. Okay? This matrix always would be satisfy the commute property, because multiply with the matrix 1A 0 1 times multiply with 1B 0 1 similar to the matrix 1B 0 1 times the matrix 1A 0 1, and this is similar because phi of 1 0 0 1 plus phi of 1B 0 1 equal to A plus B, and since Z means set of integer under addition is always abelian, so this is similar to B plus A, and since A plus B equal to B plus A, so this relation would be satisfied. So commutative property also satisfied here, because in isomorphism commutative property is if and only if condition, and we all of us know capital G is generated by this matrix, and phi of 1 1 0 1 equal to 1, and since set of integer is generated by 1, so here also generator maps to generator. So our all properties of isomorphism has satisfied here. Okay, are you getting how every property of isomorphism will satisfy if the group is isomorphism? Okay. Today I am going to say very interesting thing about permutation group. Permutation are very important. Permutation are stand for algebra. Take a finite group of order n. A finite group always contain G1, which is equal to identity G2, G3 up to Gn. And Cayley's theorem tells us every finite group is isomorphic to collection of permutation, and any set of permutation that from a group is called permutation group. It does not mean set of all permutation that from a symmetric group. In other words, Cayley says every group is isomorphic to a subgroup of symmetric group. That means if we understand the permutation group clearly, then we will construct any finite group. What we will do? We will take an object of symmetric group. Now I will define a map pi from G to permutation group, which is subset of Sn, such that pi subscript Gi with G equal to Gi times G, where for all G in capital G. Now we want to show pi is an isomorphic map to the object of permutation which is getting permuted few multiply Gi with G. Are you getting? Just think. Here I means 1, 2 up to n and actual is this is. And you will get some element which is belongs to this permuted group. Okay? Let's see the proof. Let capital G be any group and we need a permutation group. For any Gi be the member of capital G, define a map pi G1 from capital G to G by pi Gi G equal to Gi times G, where for all G in the capital G and I equal to 1, 2 up to n. Okay? Then pi Gi, a permutation on the element capital G. Okay? Now let consider Z bar. Z bar equal to set of all elements pi Gi, where Gi be the member of the group capital G and G bar forms a group under function composition. Let's see the group operation. Let G1, G2 be any member of capital G. Then what will be pi G1 times pi G2 with small g? By definition, this is equal to pi G1 times pi G2G. And by the defined mapping, this is equal to G2G. Are you getting? Okay. And that means pi G1 times G2G equal to, by the defined mapping, is G1 G2G, which is also equal to pi G1 G2G. Are you getting? Where for all G be the member of G. That means composition property has satisfied here. That means these are closed. Pi of E is the identity element and pi of Gi inverse always equal to pi Gi inverse, and function composition always associative. So Z bar from a group. Now we need to show G is isomorphic to Z bar. At first, define F by Fg from G bar such that f of G1 equal to pi G1. Now we have to show this mapping is 1 to 1. Assume Fg1 equal to Fg2. By the defined mapping, this is equal to pi G1 and this is similar to pi G2. That means pi G1 equal to pi G2. And choose an element, say G3 from capital G. By the defined mapping pi, this is equal to G1 times G3, which is equal to G2 times G3. And by the cancellation law, this is always imply G1 equal to G2. Okay? And by the construction, this mapping always onto mapping. Okay? Now we have to show is this mapping is homeomorphism. Then f of G1 G2 equal to pi G1 G2. And I have seen pi G1 times pi G2 equal to pi G1 G2. Therefore, we can write it as pi G1 times pi G2, which is equal to Fg1 times Fg2. So, the mapping is homeomorphism. So, we can tell G is isomorphic to Z bar. Okay? Well, let's see one example, Z3. And as Z3 be the all permutation from the set 0, 1, 2 to 0, 1, 2. And consider the mapping F from Z3 to S, which is equal to Fg such that G belongs to Z3. Consider a mapping F0 from Z3 to Z3 such that F0 g equal to c plus 0, where for all g be the member of Z3. What does this mean? This means 0 sends to 0, 1 sends to 1 and 2 sends to 2, and this is just identity permutation. Are you getting? Okay. Consider another map F1 from Z3 to Z3, and this is equal to F1 g equal to defined by g plus 1, where for all g be the member of Z3, and this is 0 sends to 1, 1 sends to 2 and 2 sends to 3, which is congruent to 0, and this is the 3 cycle 0 1 2. That means 0 sends to 1 and 1 sends to 2 and 2 sends to 0. Other is consider F2 from Z3 to Z3 such that F2g equal to g plus 2 for all g be the member of Z3. Then what will be the mapping? 0 sends to 2, 1 sends to 0 and 2 sends to 1, and this is also the 3 cycle 0 2 1, because 0 sends to 2, 2 sends to 1 and 1 sends to 0. Are you getting? That means this mapping only contain identity permutation 3 cycles 0 1 2 and other 3 cycles 0 2 1, and notice this is the subgroup of S3. So we can tell Z3 is isomorphic to any 3 cyclic group C3. Also Z3 is isomorphic to a subgroup A, which is subgroup of S3. Okay? Are you getting? Well, and other way is we can construct any permutation by Cayley's table, because in Cayley's table cannot repeat elements of any row and column, and for that reason every row in Cayley's table is permutation of first row, similarly column. Are you getting? So the key idea is each column or each row is a distinct permutation of the first column or first row. Let's see. Let's consider Z3. This is the Cayley table. Here the rules is, look, first element of the column is 0 and it permuted with first column 0 plus 0 equal to 0, 0 plus 1 equal to 1 and 0 plus 2 equal to 2. This is the permutation. 0 sends to 0, 1 sends to 1, 2 sends to 2. And this is actually the identity permutation. Are you getting? Similarly, second element of the column is 1. Then after operation, this will be 0 sends to 1, 1 sends to 2 and 2 sends to 0. Similarly, third element is 2 and after operation, this would be 0 sends to 2, 1 sends to 0 and 2 sends to 1, and this is the permutation, which is equal to 3 cycle. Are you getting? I think this Cayley diagram is more easiest way than this operation. Are you getting? Let's see some more example. Killen-4 group. We all of us know Killen-4 group generated by two elements A and B. Here 1 is similar to identity, 2 is similar to A, 3 is similar to B and 4 is similar to AB. And this is the Cayley table of Killenford group. We all of us know. What will be the permutation group? As before, look, column 1, first element 1. That means 1 maps to 1, 2 maps to 2, 3 maps to 3 and 4 maps to 4. And this is the first permutation. Are you getting? This is only identity permutation. Second is column 2. Next element of column 2 is 2. Here 1 maps to 2, 2 maps to 1, 3 maps to 4 and 4 maps to 3. That means this is similar to this. 1 maps to 2, 2 maps to 1, 3 maps to 4 and 4 maps to 3. And this is similar to 2 transposition. 1, 2 with 3, 4. Okay. Let's say column 3. Here the next element 3. 1 maps to 3, 2 maps to 4, 3 maps to 1 and 4 maps to 2. See, this is the column 3 and this is also 2 transposition 1, 3, 2, 4. And fourth is the element 4. Here 1 maps to 4, 2 maps to 3, 3 maps to 2 and 4 maps to 1. Just look. And this is equal to cycle 1, 4 times cycle 2, 3. And this is all permutation. Identity and 2 cycle. Therefore, our original group EABAB have transformed identity 2 cycle 1, 2, 3, 4, other 2 cycle 1, 3, 2, 4 and other is 1, 4, 2, 3. And these permutation are actually Z2 direct product Z2, which is subgroup of S4. So we can tell Killenford group is isomorphic to group of permutation Z2 cross Z2, which is subgroup of S4. Now let's see one more example. The group of complex fourth root of unity under multiplication, which is isomorphic to group of integers modulo 4 under addition. This is the Cayley table. We all of us know all structures same all by Cayley table, only the elements are different. Here the elements match to table according to colors. So they are isomorphic to each other because their Cayley table are same. Okay? We all of us know. I have discussed it elaborately in my previous video. Now let's see what is the permutation group of the group of complex fourth root of unity. We all of us know this is the Cayley table. I have considered here 1 is 1, minus 1 as 2, I as 3 and minus I as 4. Then by Cayley table, the column 1 is 1 maps to 1, minus 1 maps to minus 1 and I maps to I, minus I maps to minus I. That means this is just identity permutation. Second columns 1 map to minus 1, minus 1 map to 1. That means by this here 1 and minus 1 I have considered as 1 and 2. That means this cycle 1, 2 and I maps to minus I and minus I map to I. So this is composition 3, 4. That means second column is similar to cycle 1, 2 and cycle 3, 4. Okay. Third column is similar. 1 maps to I, minus 1 maps to minus I map to minus 1, minus I map to 1. That means this is the cycle 1, 4, 2, 3. Okay? And the fourth column is 1 map to minus I, minus 1 map to I map to 1, and minus I map to minus I. That means this is the cycle 1, 3, 2, 4. This is the actual set. So consider this permutation as capital S, which is, notice, this is the subgroup of S4. That means the group of complex fourth root of unity is isomorphic to this subgroup capital S, which is subgroup of S4. Are you getting? Well. And the element of this subgroup behave the same way with the actual element of the group. Are you getting? Why permutation are stone of the finite group? And if I represent each cycle by a permutation matrix, then it will be first 4 cross 4 identity matrix. This is, and the cycle 1, 2, 3, 4 represent the matrix 0, 1, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Okay? The cycle 1, 4, 2, 3 represent the matrix 0, 0, 0, 1, 0, 0, 1, 0, 1, 0, 0, 0, 0, 1, 0, 0. And cycle 1, 3, 2, 4 represent the matrix 0, 0, 1, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 0, 0, 0. And this is the subgroup of 4 cross 4 invertible matrix. Okay? And this matrix behave as same subgroup capital S and also behave as same group capital G. Because we can represent any group as permutation and we can also represent any permutation as a matrix multiplication. Okay? And this is in linear algebra matrix representation theorem, which states any group can be represented as by matrix. Actually, abstract algebra is stone of linear algebra.